everyone. Welcome to the BayesOpt Speaker Series today. And today we have the pleasure of having Ilija Bogunovic joining us, our speaker. And so Ilija is an assistant professor at the Electrical Engineering Department at University College London. Before that, he was a postdoc at ETH Zurich and received his PhD from EPFL. Ilija has done really awesome work in areas including data efficient, interactive machine learning, sequential decision-making under uncertainty, experimental design, active learning, as well as reliability and robustness in data-driven algorithms. And today, he will tell us about robust design discovery and exploration in Bayesian optimization. Great, take it away, Ilija.
Thank you very much, Steve, for the kind introduction. So, hello, everyone. It is a great pleasure to give this talk today. So at the beginning, let me first start with a little bit of motivation for today's talk. Nowadays, we face a lot of exciting real-world problems in both science and engineering, such as, for example, protein design, drug and material discovery, tuning of various robotic tasks, and many others. So one common thing for all these problems is that we often want to discover some optimal solution. So for example, in drug discovery, we'd like to discover a drug with certain therapeutic properties. Maybe in material science, we might seek to discover new materials that have certain good properties, for example, sufficient levels of elasticity or similar. And in robotics, we might be interested in searching, say, for best performing hyperparameters. So the main idea of how we want to bridge the gap between machine learning on one side and science and engineering on the other is that we want to automatize this discovery process. And in particular, based on previously collected data, we want to learn to design a sequence of experiments or trials, which then basically directly translates into gathering new data. And basically, the goal is to adaptively select experiments that are the most informative about the quantity of our interest. And so what are the main challenges in these applications, and why are we not yet there? Well, typically, the search space is very large. And this is both the case with potential drug-like molecules, but also when searching through, say, neural network architectures and hyperparameters. Right, so we might suffer from combinatorial explosion of designs or just work in a very high dimensional spaces. Another challenge that is pertaining to data collection processes is the fact that typically data is very costly and we sometimes work with noisy experiments. So in response to that, we often seek to minimize the number of trials, which then translates into number of data points or samples that we seek to acquire. And since data is often expensive, apart maybe in video games, our goal is to enable the efficient automatic data collection process. And we'd like to be able to provide some sort of statistical guarantees, and we would like to minimize number of samples or trials. Besides these guarantees, some other types of guarantees that practitioners might seek, they're often related to all kinds of robustness requirements. This is, for example, crucial in, say, safety critical applications. Just think about it, for example, when, say, optimizing the design, manufacturing, and operation of our aircraft. In that case, we also need to pay attention to various robustness aspects, right, and challenges such as out of distribution and distributional shift challenges, transferring from simulation to reality, time variations, potentially corrupted and confounded data, and many other robustness aspects that might be of interest in these applications. So in general, the ultimate goal is to design rigorous, efficient, and robust learning methods, that are able to tackle these types of problems. And in today's talk, we're going to look at the previously mentioned problems through the lens of Bayesian optimization. And because this is the seminar series on Bayesian optimization, I'll just do a brief recap on Bayesian optimization. So the main problem that we care about in Bayesian optimization is sequentially solving the black box optimization problem. So in particular, we have this black box objective that is noisy and typically costly to evaluate. And at each round, we would like to select a point xt to evaluate this objective. And then we receive this noisy evaluation yt. So the goal is to sequentially learn and optimize an unknown function simultaneously. Now, one of the issues is that having a finite number of data points, various functions can actually explain our data, right? So typically in Bayesian optimization, we encode our prior beliefs about the true unknown function through Gaussian process prior, right? That is, again, sort of parameterized by a kernel or covariance function that sort of dictates the smoothness of the sample paths. Now, having our Gaussian process model, say, then we typically build an acquisition function that typically tells us how good some point is to evaluate, right? So typically we optimize an acquisition function to decide which next point xt to query. And throughout the history of Bayesian optimization, various acquisition functions have been developed, right? So you can see some of them here on this particular slide, although this is definitely a non-exhaustive list of acquisition functions. Now, to measure the performance in Bayesian optimization, we typically look at cumulative regret, right? So cumulative regret sort of captures this notion of exploration exploitation, because we want to discover the global maximizer, but we also need to pay attention of exploiting in the sense that our subsequent points that we picked need to be sort of close to the global maximizer, right? And the property that we see here is sort of, we want our algorithms to be no regret, meaning that the average regret goes to 0 as the number of samples goes to infinity, or number of rounds. On the other hand, we also have this simple regret metric that simply tells us, well, we're going to play this Bayesian optimization game for t rounds, and then after t rounds, we're just going to report a single point, here denoted as xt hat, and we want this design or point, right, to be as close as possible to the global maximizer. Now, a very useful concept that is often used in Bayesian optimization and that we're going also to make use of today is the so-called confidence bounds. So what's the main idea here? Well, say that we have already observed t data points, then we can use our Gaussian process posterior or kernel breach regression estimate to estimate, say, the posterior mean, mu t here. And now the idea is that we want to construct confidence bound such that our true function, f, is within the confidence bounds, say, with high probability. So the confidence bounds here, we have the lower confidence bound on the left and upper confidence bound on the right. And they're simply just a sum of the posterior mean plus minus the scaled standard deviation of our posterior standard deviation, right? Which also, you can think about it as the uncertainty that's related to our process. And so one important parameter here is this beta parameter that sort of controls the width of confidence bounds. And depending on the algorithm and the underlying assumptions, different works have been using different widths. So for example, the famous GPU-CB algorithm, it sets this confidence width parameter to scale as with the complexity of the function f, with the noise model in our observations, but also this kernel-dependent maximum information gain, right? Which is simply the quantity that tells us what's the maximum information gain that we can acquire about the Gaussian process model, but at t different points, right? And of course, depending on the kernel, we get the different rates for this parameter. All right, so now that we have these confidence bounds in place, a very nice property of these confidence bounds is that having more data, having observed more data, well, these confidence bounds are shrinking, right? And we're slowly learning about the true underlying function. And it turns out that, you know, we can also compute these confidence bounds in some cases for graph functions, and we can go beyond non-Euclidean domains and consider graph functions that are defined on graphs. And we can also use graph neural nets as our estimators. So in general, these are very important concepts in Bayesian optimization, and many algorithms make use of them. All right. So now that we have some of the tools in place, I'd like to tell you a little bit more about how to discover provably robust designs in Bayesian optimization. So a lot of work has been done on non-robust Bayesian optimization, but not so many works have actually looked into robust Bayesian optimization. So what's the problem here? So say we have some objective function that is now parameterized in terms of x and c. So x is the decision variable. So say that f is, for example, the amount of energy that's generated, x might be the height of air wind turbine, and c might be a weather condition, right? So c is just the contextual variable that basically that we want to be robust with respect to. So here the goal is then to discover robust design x by sequentially designing experiments and querying this function f that is unknown. And some examples where this is of interest is, for example, when we are transferring from simulator to the reality, and we want to close this sim to real gap, or again from simulator to reality, there might be some sort of time variations. There might be input perturbations, implementation errors, and all kinds of things that we might want to be robust with respect to. So this problem formulation is very general, and it can sort of encapsulate some of the very nice and interesting problems. So let's look at some of the specific problems. So consider the following example. This one is known as group robustness, where we would like to find where the input space is partitioned into groups, and we would like to identify the worst case optimal group. Considering an example where you maybe want to build a personalized recommender system, and you'd like to discover a group of movies, right, to recommend to the user whose preferences are known, such that even the worst movie from within this group is sort of up to the liking of the user. Some other examples include robust design discovery. So here's the following example. Consider, for example, optimizing this blue function on the left by using a simulator, right? So by running a standard Bayesian optimization, we might converge to the global optimizer, right? That corresponds to this optimal function value. But you can see that this function value is very picky, right? So maybe if you go to reality from simulator, the function might just perturb just a bit, might look like the red one here on the right-hand side. And what can happen then is that the performance of the reported point degrades significantly, right? So in this case, it might have been better for us to report, say, this robust and local maximizer instead, right? So this can be nicely formulated by using this mathematical formulation where we want to discover a design that is robust with respect to the worst possible perturbation. So a good thing is that, we can have a single algorithm that can tackle all of these cases with very subtle modifications. And I'd like to tell you a little bit about this algorithm. So we call it StableOpt. So StableOpt combines optimism with pessimism. And at every round t, it selects a point xt, right? That is max mean optimal in terms of the objective, right? But the issue is that, of course, our objective is unknown, right? So instead of the true objective, we are being optimistic here, and we are using upper confidence bound that's basically computed based on previously observed samples. Then in the second part, we are computing the context variable that is worst case, that is basically the worst case realization of the context variable for the reported point xt, right? But here we are being pessimistic, meaning that we're using the lower confidence bound of the true function, right? So we really want to find the worst possible perturbation, and we are sort of being pessimistic about it. So this algorithm explores both decision spaces, right? Both the x space and the c space. And then we simply query the unknown function at the point xt, ct, right? And we update our Gaussian process model in a standard way. Right, so what's going under the hood here is that this algorithm basically builds a set of plausible robust maximizers and proves out the remaining of the space. We can use this algorithm to probably discover near optimal robust solutions under certain regularity assumptions on the objective. Either function f is sampled from a Gaussian process, or it has a low reproducing kernel Hilbert space norm. So the main idea here is that we run our stable opt for capital T rounds, then we can report a suitably chosen point x capital T, such that the robust simple regret is at most epsilon, right? Epsilon is the precision that we want to achieve. So this robust simple regret is simply the difference between the optimal robust value and the value, the worst possible value for the reported point. And now we can actually look at the sample complexity rates. They depend on the precision that we want to achieve. They also depend on the confidence intervals, and they depend on the model capacity that we're using. Of course, the more smooth function, the more smooth kernel function that we use, we're going to need less samples to achieve epsilon suboptimality. And of course, we can instantiate this for different kernels, right? For square exponential, maternal, and so on. And this result actually nearly matches the lower bounds that we also obtained. Okay, I will skip the analysis steps for the sake of time, but the bottom message here is that all the steps are necessary in the algorithm, since the analysis tightly depends on the rules for selecting points. All right, so in many applications, we realized that we don't only seek to find a single robust design, but instead, we might want to find an entire robust distribution over designs. So consider the following example, where we have an autonomous vehicle and human vehicle driving on the same road. So we might want here to find an overtaking strategy that is robust against worst case human behavior, right? So we're basically trying to find a strategy for the autonomous vehicle. And a lot of these interactions in traffic that involve humans and autonomous vehicles are modeled in a game theoretic style, since humans can be sometimes adversarial towards autonomous vehicles, right? For example, not letting them to overtake or merge in a dense lane and many other situations. So how do we model this? Well, we are optimizing over all the probability distributions over the trajectories for the autonomous vehicle. So the trajectories are given in yellow here. And we want to be robust with respect to the worst possible trajectory for the human vehicle. And you can think about this function f being sort of the unknown expert's preference, right? So we want to use the help of expert to design, to discover robust trajectories. So this expert might, for example, reward the progress of the autonomous vehicle, but might penalize if it's braking or very close to the human vehicle, and etc. Right? So what's the key idea behind tackling this problem? In the essence, we want to execute no regret dynamics of this game, and for this we developed a new algorithm, GP-MRO. So let me tell you the main ideas behind this algorithm. So in the essence, we again make use of these shrinking confidence bounds that you've seen before. And then we want to find the robust solution by using an online learning algorithm for playing this game. The problem with using online learning algorithms is that they require a full information feedback that is not available in this case. Remember that we only get to see single point observations. So the main idea here is that we want to hallucinate the full information feedback by using our confidence bounds, right? And this is precisely the main idea of our algorithm. So what we do here, we sort of formulate a fictitious game, right? So we play first for the second player. We essentially use exponential weights method, like a standard methods in online learning, and prediction with expert's advice to choose a distribution over parameters theta, right? So intuitively here, we're using a sequence of previously seen UCP functions that are known to us because they're model-based, right? And you can think of this as, those designs that performed well over the course of the run, their weight will be higher, right, than those that performed poorly, and exponentially higher, in fact. So that's how we obtain the distribution over the designs, right, over the second variable. And then the first player just simply best responds to this distribution, right, by using, again, upper confidence bounds instead of the true unknown function. Finally, we perform additional exploration given the first parameter xt, right, to sort of minimize the uncertainty. And it turns out that by doing so, right, and querying the unknown function at points xt theta t, right, we can come up with the distribution. So the output distribution is just a uniform distribution over the designs. And it turns out that this distribution is robust, and we can achieve the similar performance, right, with similar sample complexity rates as in the stable opt algorithm, but this time in terms of the robust distribution. Okay, so let me just show you how this looks like in the animation, right? So we actually tried this on a simulator. So in the bottom, you can see the stable opt algorithm that is worst case robust, and its strategy is deterministic and it's overly conservative, so it always ends up breaking behind the human. While this other algorithm, GPMRO, it basically implements this mixed strategy approach, sometimes overtaking from above, sometimes from below, but sometimes even breaking behind the human, right? So here, half of the times roughly the algorithm is successful in overtaking the human model. All right, so I hope I gave you a little bit of intuition about the robust Bayesian optimization, right? So this is a powerful framework that we can use to discover robust designs, or for example, robust mixed strategies, right? But also one more work that I didn't talk about today is how to be robust against distributional data shifts, right? So this is the third box here. And if you're interested to know more about this, please check out our paper. So in the essence, we can use versatile robust objectives, and we can provide data efficient guarantees, and plus statistical learning guarantees. All right, so maybe I can pause here if there are some questions.
Yeah, I had one actually. So the performance of most of the robust algorithms depend on also on the gap between the best possible solution, the best robust possible solution. Is there any way to try to estimate this gap, taking into account that exploring dangerous solution is dangerous by kind of definition?
Mm-hmm. I see. So this gap is just this is something that's not used by the algorithms, right? So this is just suboptimality gap that's used inside the theory, right?
Usually, the suboptimality gap depends on some parameter of the algorithm that decides how robust you want your solution to be.
Oh, here, sure. So basically here we fix this parameter, right? In the theory, we assume that this suboptimality gap that we want to achieve is sort of fixed, right? So this is just a constant, right? It does not depend on anything. This is the precision that we want to fix. But I think your question is more related on how to estimate, maybe in this example, right? I can tell you about this.
Yeah, the question was mostly how do you estimate the right robustness threshold to achieve performance, taking into account the fact that if I start by looking at a threshold that's maybe too high, I might break a robot or crash my plane or whatever.
Right. So I guess your question is related to this parameter here, epsilon, right? That should probably be something different, like different symbol, right? So basically, how to know this? How do I know this parameter before starting the optimization, right? Procedure in the first place, right? So basically, there's no good answer to that, right? So we assume that's the input to the problem, right? On the other hand, there are a lot of works that deal with safe exploration, right? Which is not the case here, right? Even in safe exploration, you certainly need to have some sort of assumptions on the unknown function, say for example Lipschitzness, and then you might actually try to seek, right, whether your confidence bounds are below some certain safety threshold, right? But here we don't deal with safe exploration, in fact, right? So here we assume that, for example, this uncertainty set that you're considering when optimizing is basically input dependent, right? So it's specified by the user. You're the one who specifies the amount of robustness that you want to achieve, for example, in this particular problem.
Okay. It makes sense also in a lot of engineering application that's specified by some regulation or something. So that's how you
Exactly. In distributional robust optimization, you have these uncertainty sets that are basically sort of design choice.
Yeah, so I guess I just have like a follow-up. Maybe not that much of a question. So I feel like this epsilon can probably also be estimated if we have enough data about like how much noise there is when we're evaluating the function. But I'm not exactly sure like if it's a perturbation in the input space. Do you have like any insights on like if we were to estimate it, what kind of we should obtain?
So for example, I think there might be it's great to clarify this. I think so pretty much this epsilon is something that's related to the test time, right? That you don't have access to, right? So you know, say here in this example, you're working with a simulator, right? You know, so these are perfect conditions, right? So you don't know how much of the input perturbation you're going to suffer at the test time, right? So it might be, you know, it might be hard to estimate unless you're working with the real system, right? If you're working with the real system and you get to observe, you know, well, even in the if you're working with the real system, that I guess, you know, by querying the function, well, I think if you're working with the real system, perhaps you can then estimate it. But the idea here is that you're actually working with the simulator, right? And you have no idea. You might have prior beliefs on how to set this epsilon.
I see. Cool, thanks.
All right, so let me just briefly show you like one very brief application of these approaches to robust model-based RL. So this is a classical model-based RL setup where we want to discover optimal policy by maximizing some performance guarantee, right? For example, some of the received rewards within the episode. And here, basically, our dynamics, right? Transition dynamics are known. They depend on the current state and the current action, and then maybe some system noise, and then we transition to the next state. And of course, action is the result of our policy applied to a state. Now, just a learning protocol here is that we have some acquired data. Then we can, for example, try to learn the well-calibrated model, right? Say a Gaussian process, and that has some confidence bounds. And then we can use the model within the policy optimization, right? To actually optimize for the policy on the model, right? Then we use this policy, we roll out the policy in the real world, and then we collect more data. And so this loop, you know, sort of repeats. Now, one challenge with this is that the resulting policy is often non-robust, right? And basically, if we are going from training to the test time, right, you know, there might be certain conditions that are not captured, right? And to be able to model all the uncertainties, what we do, we make use of an adversarial agent that sort of applies disturbances to the system. So this can be formulated as the robust policy optimization problem, where we additionally have a adversarial policy pi bar. So our objective now depends on the policy pi bar, adversarial policy, right? And the transition dynamics also depend on the adversarial action that's played by the adversarial policy, right? So we can try to do this during the training time, and it turns out that we can still combine pessimism with optimism, right? And we can produce a stable opt-like algorithm that we, in this case, call RHUCRL, right? But this time, right, not in terms of the designs, but in terms of the robust policies. So we tested this algorithm on some of the famous Mojoko environments, right? And here we looked at the worst case return, right? So we return the policy, and then we look at the worst possible adversarial policy for the return one, right? And then we compare our algorithm against robust heuristics, against some non-robust model-based RL, and deep robust reinforcement learning that uses 5 times more samples than our approach, right? And here the goal is basically to learn these robots, right? Like say half cheetah to walk, but then there's the adversary that sort of applies disturbances, right? By, for example, you know, applying force to the ankles of these robots, you know, making them very hard to learn to walk, right? So that's what we do at the training time, and basically to capture this first case return, right? So in all these environments, our algorithm actually outperforms all the other baselines, right, in terms of the worst case return. But one interesting thing that we also observed is that if you were to look at the average return, right, something that our algorithm is not designed for, it turns out that this sort of adversarial training actually helps out even on average, right? So we can see, for example, in the last example, that our algorithm often improves this non-robust performance even.
Can I ask a question?
Yes.
In these, are you using GPs for these experiments?
Yes, we're using GPs to learn the dynamics, right? But then, to optimize the policy, we are resorting back to the deep robust RL methods, right? So basically, you can use a model-free RL methods once you have a known model dynamics.
I see. So you'll just sample. Are you adding any extra exploration terms, or it's the same as what you did in StableOpt?
So it's pretty much the same what we did in StableOpt. So the main idea here is that you're building the model, right? And then you're feeding the model to the solver, which is a model-free deep robust RL, right? But now this algorithm interacts with the model. It no longer queries the true samples from the environment.
I see. And then what about choosing the kernel parameters? Is that that's assumed known, or you do learn those online too?
We learn them online. Yes.
I see. Is there like a warm-up stage where you like do maximum marginal likelihood on, like you do some random exploration, fit the kernel in and freeze it?
Exactly. Okay. Yes.
Okay.
Thank you.
Cool. Thank you.
Okay, so this is just an example of how these sort of methods were applied to the model-based RL. And so far, we looked at the case where noise is, say, IID, Gaussian, or sub-Gaussian. So now I'd like to go beyond this assumption and tell you about Bayesian optimization when our data is corrupted or, say, adversarially attacked. Right, and this can happen in many real-world applications, including click frauds, fake reviews, ratings. Like in engineering, we often get outliers from sensors and so on. Right, so this problem has been looked at in the multi-arm bandit literature. So I can show you the protocol because we're going to use the same protocol. So the algorithm plays the action, and then the attacker intercepts the action and pretty much poisons the reward, right? And the learner then observes this confounded reward. And it's supposed to learn from this. Now, in terms of the Bayesian optimization, you can think about having a unknown function, right, that has a global maximizer, and consider that there's a hidden adversary that only corrupts in this region where the true global maximizer lies, right? So it turns out that only a few corrupted samples in this region can actually, can actually make the algorithm to eliminate this region, as there's no global maximizer there, right? And the algorithm can, for example, converge to some other suboptimal point, right? So in that case, achieving linear regret in the essence. And this is pretty much the case what happens with the famous GPU-CB algorithm designed for the non-robust performance, right? You can basically see, so this algorithm picks point at each time t that maximizes the upper confidence bound, right? But the problem here is that confidence bounds are non-valid, right? So this algorithm lacks robustness, and the few examples are just going to, degrade the performance of this algorithm. So here is a very smart idea that allows us to alleviate this. Well, let's just, enlarge these confidence bounds, right? So that they're not invalid, right? So here we're using the biased estimator, right? So this biased estimator is computed based on the corrupted rewards, right? But now what we do, well, we're going to increase the width of our confidence bounds, right? So we're going to use the standard width, right? That's sort of used in the GPU-CB, but we're going to enlarge it by this factor that's proportional to the total amount of corruption. So this C is the upper bound on the total corruption injected in the system. Of course, if the adversary has an unlimited budget, there's nothing you can do, right, about it. So what we need to argue about the performance of the algorithm with respect to the budget of the adversary, right? So what happens here in the right, on the right-hand side in the picture, you can see that after the adversary exhausts its budget, the algorithm is able to recover and to converge to the global maximizer. So that's the main idea. And for this algorithm, we are also able to provide standard cumulative regret bounds. So here, the regret bounds depend on, they basically are addition of two terms. The right-hand side is the non-corrupted regret bound. So this is just the standard regret bound that's basically achieved by the GPU-CB algorithm. But now we have this other bound, right, that is due to corruption. We can see that the regret bound scales linearly with capital C with the adversarial budget, right? But still, for some values of C, it can the total regret can be sublinear, right? Now, the main observation here is that we can bound the difference between the non-corrupted, right, the posterior mean that's computed based on the non-corrupted samples, and the posterior mean that's computed based on the corrupted samples. And it turns out that this difference is precisely the one that we use to enlarge the width of the confidence bounds. Now, the question is, right, can we do better, right? Can we achieve a better multiplicative joint dependence in the regret bounds, both in terms of C and T, right? So here, for example, if C scales as, say, square root T, right, the regret is automatically linear. And it turns out that we can, right? So in our newest paper, we propose like a new corrupted mean estimator. So this mean estimator is computed, right? It's basically has the same form as the standard, GP posterior mean, right? But now what we do, well, we form the observations a little bit differently, right? In the essence, what we do among the query points, right? If there are more points that are sampled multiple times, we average out the observations. So what's the intuition behind this? Well, the intuition is that if the same action is played multiple times, then it becomes harder for the adversary to hide the true value. Since the rewards of the same played actions are average, the adversary needs to spend more of its budget corrupting the rewards. And that's the main intuition behind this robust mean estimator. And so for this one, we provide the novel confidence bounds that hold with high probability. So here we basically bound the absolute difference between the corrupted mean estimator and the true function. And now we can see that basically we have this term. So here U min is the minimum number of times any action is being played, right? So what we're doing, we're sampling the same action multiple times. That's going to be our idea, right? And of course, the more times that we sample the same action, suboptimal action, we are going to suffer in terms of the regret, right? So here we additionally, besides exploration exploitation dilemma, we also have this robustness dilemma, right? So these confidence bounds, we will typically apply these results with, with this term that multiplies adversarial budget being much smaller than 1. Okay, so I'm going just to outline like key ideas behind our algorithm. So it's the algorithm consists of a few ideas that are sort of stacked together. So let me try to just give you like a high-level intuition of how the algorithm works. So the algorithm now basically runs in episodes of exponentially increasing length. And at each time step, it selects a point xt that simply is the most uncertain about, right? So it maximizes the posterior standard deviation. So this set xh is basically, you can think about it as the set of points that survived up to episode h, right? So these are the points that still have a chance of being maximizers. And I'm gonna say a little bit more about that later on. Now, one thing to note is that this sigma depends on the t prime data points, right? While our current time step is t, right? So t prime is strictly smaller than t, right? So what we want to do, we want to perform the idea of rare switching, meaning that we're going to not update sigma at each round, right? But we're going to be a bit smart about that and only update sigma after some point has been sampled enough times, right? So the condition for updating sigma, right, is given in parentheses. So you can think about this as the exponential information gain, and information gain dictates the regret guarantees. So the intuition here is that basically we're looking at the information gain at by using all the t data points, and the information gain by using only t prime data points, and we're not allowing this the ratio between these two to be too big, right? So just intuitively, we are sacrificing a little bit of information that we are missing, right? But on the other hand, we're increasing sort of the robustness. So that's the idea here. Now, this is only a subsampling approach. Now that we have our set of points queried in in the way that I just explained. Then we query each distinct point from within this set proportionate to how many times it was selected. And we also ensure that each point is queried some minimum number of times, right? So that, we get the information about all the points. And then we just simply receive observations and we update our GP model in the standard way. And then we use the confidence bounds that I've shown you from the previous slide to basically update our set of points, right? And this is used in the standard ARM elimination procedure that's used in the bandit literature. In the sense, like all the surviving points are those for which upper confidence bound is larger than the maximum lower confidence bound.
Can I ask another question?
Yes.
I wonder if you considered an alternative algorithm which would be use the standard GP but modify the likelihood to be a robust likelihood, like a student distribution or something. Because this rare switching feels like a bit of a hack. Like you said, you're losing information. Why not just do the statistically optimal thing under the assumptions that there are outliers in the data?
Well, interesting. Yeah, I think.
I mean, inference is harder, right? But like whatever, there are standard solutions to non-conjugate GPs, right? So that and then you can use off-the-shelf exploration algorithms for them.
I think that's an interesting idea. To be honest with you, like we haven't explored that direction, but I definitely think that this might be also one way to go as well. I agree with you on that.
One advantage,
we haven't explored it.
Okay, thank you.
One advantage to not switching is actually that this way you can like aggregate the feedbacks and you can perform inference in the GP much faster. Because essentially at this point, since all the points are the same, you can replace them in the GP with one single point that's equivalent, and computation is much faster.
Exactly. And if you care about to see that, please check out Danielle's paper on this. Very nice procedure for basically saving computation by averaging these samples. That's correct. Yeah, I agree with that. Yes.
Yeah. So for this particular problem, how does it relate to Bayes optimization with heteroscedastic noise? And I wonder,
yes.
like, yeah.
So basically, I think that the main difference is in the heteroscedastic noise, it is still a stochastic setting, right, where your noise distribution depends on the queried points. But here, in fact, right, like the observations can be, are non-stochastic, right? They're adversarial, right? So this is the important difference.
I see. So it's actually the there's a adversarial attacker.
There's an attack by the adversary. So adversary knows the true function, can see the action that you played, and can then perform the corruption based on that knowledge, right? So, which is completely different than the heteroscedastic setting.
Got it. Yeah. Thanks.
All right. And it turns out that with this algorithm, we can actually improve the performance, right? In particular, we managed to get rid of the square root t dependency in the first term. So now we have gamma t to the power of 3/2, right? And this strictly improves the upper bounds for all the popularly used kernels. Unfortunately, this is still a bit non-optimal in comparison to the lower bounds, right? So I think basically we can probably improve this to c times gamma t instead, right? But this is still an open question. I think a little bit of more precise analysis could essentially fix this, but still an open question. All right. So this is all what I wanted to say about the corrupted observations. Now, let me just tell you a little bit on the experiments, right? So what we did here, we actually experimented with different attacks. So we were actually attacking Bayesian optimization algorithms. So here on the left, you can see the classical GPU-CB algorithm. You can see that in blue, it is its performance when there are no attacks, right? But when there are attacks, even the second best attack from the set of attacks that we applied, right, significantly degrades the performance of GPU-CB. On the other hand, you can see that our algorithm actually maintains the performance, right? In this particular example that we looked at, and basically over the duration of the optimization, it sort of achieves similar performance. So we can also try to look at this at the cumulative regret curves, right, for the standard GPU CPU. So we try to attack it with different types of attacks. Just for example, maybe like whenever the algorithm selects a point in the region where the global maximizer is, we sort of reduce it to some specified threshold. That's one type of the attack. Another type of the attack is just to flip the reward. So for example, if it gets reward 1, then we just the adversary pushes it back to -1, and so on and so forth. So we experimented with different attacks, and you can see clearly that GPU CPU achieves linear regret, right? So it's highly non-robust. On the other hand, our algorithm achieves sublinear regret for all the considered attacks, and also the algorithm that performs a bit worse in terms of theory, this robust GPU CPU, also attains sublinear regret and even a better performance. So there might be still some gap between theory and practice, maybe in the constants that are not optimized or similarly. But at the end of the day, our algorithms, they achieve these sublinear cumulative regret guarantees despite a certain amount of corruption that's injected in the system. All right, so that'd be pretty much everything that I wanted to tell you about today. So besides what I've shown today, there are many other exciting directions when it comes to Bayesian optimization, right? And that are at the intersection of robustness and efficiency, in particular in active learning and these related fields. Just for example, one can try to be robust. Typically in practice, we work with, misspecified models, right? We might have like a misspecified model, or for example, there might be a misspecification in the specified prior. So we might work with with the wrong class of functions in the first place. And in that case, we might want to be robust with respect to that. I think you heard a little bit about the risk-averse heteroscedastic Bayesian optimization last time. So this one is interesting because here, besides exploration and exploitation, we might also want to balance risk. And I think there's also, in general, there's also a line of research where we're interested in creating efficient attacks, and probable defenses. That might also be interesting for future work. So here's the list of the main references of today's talk. And finally, this is the list of my collaborators, without whom this work wouldn't be possible. And with this, I'd like to conclude and to thank you for listening.
Yeah, thank you so much, Ilija. This is a really great talk. And
thank you.
Yeah, so for the audience, please raise hands if you have questions.
For the work on the adversarial attacks, I was thinking another thing of picking a switching rule based on just looking at the ratio of log determinants rather than doing some more advanced statistics is because it doesn't depend on what the adversary is doing during the round.
Exactly.
So that's by design, or it's a side effect, or like it's known that all methods that deal with adversarial attack have to not look at the feedback, or
yeah. Yeah, that's a great observation. In the sense, this condition that we're looking at, right, and the way that we're selecting the points does not depend on the observations, right? So this is pretty much like ignorant of the observations. So in our algorithm, we only receive observations at the end of the episodes, right? And basically the selection rule does not depend on the observations within that particular episode. This also allows us to use a tighter confidence bounds when it comes to the non-robust setting, right? Because like we're essentially using a non-adaptive confidence bounds in this approach.
But it has to be done because otherwise the adversary would exploit whichever kind of adaptivity you have.
Exactly. That's my intuition about it, right? If I don't know if there would be some other approaches that actually use the observations to make the decisions, but like by doing this sort of active exploration type type of the acquisition function, right? We are basically avoiding relying on the observations until necessary, which is the end of the episode.
One less problem. Good.
Yeah.
Thanks.
Thank you.
So I have a maybe more general question.
Yes.
So we've seen like a lot of really nice algorithms and formulations on how to be more robust. And so what do you see as the next step? Like, what are the open questions in this field that are critical to, say, like real-world deployment?
Well, I think there are, besides these robustness questions, we also mentioned this issue of safe exploration, right? If you're actually exploring on the system, right? In that case, you also need to pay attention on how you select your actions at each run, right? So maybe like one can think about the combination of safe exploration plus robustness, right? That could be like another way of being even more safe, right? But in general, I think basically I think it's very important, right, to sort of because a lot of things nowadays, if you also think about, say, this nuclear fusion research going on, right? A lot of things are done on the simulators, right? And then we take our designs or policies and we implement them in the real world, right? So in that case, I think it's very important to sort of be able to bridge this sim to real gap, right? And to be robust with respect to everything that might occur in the real world, right? And I think a lot of these questions are also application dependent, right? In different applications, we might care about different things and being robust to different things. On our side, we definitely want to have like a toolbox for performing like the black box optimization with Bayesian optimization, right? By being able to tackle all these different problems. But various other questions, right? One can think of, right? Getting the, as I already shown, like getting this to the reinforcement learning framework is definitely one of them. I don't think much work has been done on that part either.
Yeah, all these are super important. Yeah, thank you, Ilija. Thank you again for giving this really nice talk. And
thank you very much.